everyone, welcome to the lecture series on information theory and coding. Myself, Professor Meenakshi Thurse, Department of ECE, KLS VDIT Hadia. So in the previous lecture, we had solved few examples on Shannon's Fano binary encoding algorithm and Shannon's Fano ternary encoding algorithm. So in this lecture, we'll solve few numericals on Shannon's ternary encoding algorithm. So consider an source S which emits two discrete symbols S1 and S2 with probabilities 3 by 4 and 1 by 4 respectively. Obtain Shannon-Fano code for a source S, its second and third order extensions. Calculate efficiencies for each case. So the first step for Shannon's Fano encoding algorithm was to arrange the probabilities into two groups. So first we need to arrange the probabilities in decreasing order and then group the probabilities into two sets such that sum of probabilities in both these sets is almost equal, and we need to assign 0 to the first group and assign 1 to the second group, and this step has to be repeated till no further division is possible. So in this problem statement we have two symbols S1, S2 with probabilities 3 by 4 and 1 by 4. So we need to determine the code word for source S and code word for its second order extension and third order extension and determine efficiencies for all three cases. So once we arrange the probabilities in decreasing order, the order is as follows. First we'll have 3 by 4 and then 1 by 4. 3 by 4, the symbol is S1 with 1 by 4 probability symbol is S2. So since we have only two symbols, we'll have two groups. 3 by 4 will be one group and 1 by 4 will be in the second group. The first group will be assigned with 0, second group will be assigned with 1. So symbol and their probabilities are written in this table. So 3 by 4 the code word is 0, 1 by 4 code word is 1, and both the code words are of length 1. So we need to compute the source efficiency or the code efficiency. Efficiency is given by entropy by average code word length, whereas entropy H of S is given by summation I equals to 1 to n probability log of 1 by probability, where n represents number of source symbols. We have two symbols, therefore capital N value is 2. Therefore entropy formula is summation I equals to 1 to 2 probability log of 1 by probability to the base 2. Base 2 because it is a binary encoding algorithm. The first probability is 3 by 4. So we'll have the first term as 3 by 4. Log 1 divided by 3 by 4 can be written as log 4 by 3 to the base 2, and the second term is 1 by 4 log 1 divided by 1 by 4 can be written as log 4 to the base 2. So once you simplify this, we'll obtain entropy as 0.811 bits per symbol, and the average code word length is given by summation I equals to 1 to n pi li. N value is 2 because we have two source symbols. Multiply the probability value and its corresponding code word length. So 3 by 4 probability and its corresponding length is 1. So we'll have 3 by 4 into one term. Similarly, for the next symbol, probability is 1 by 4 and its length is 1 again. So we'll have 1 by 4 into one term. So once you simplify this, the average code word length is 1 bits per symbol. So in order to compute efficiency, substitute entropy and average code word length, and we'll obtain the efficiency as 81.13%. Same thing has to be done for second order extension of a source and third order extension for a source. So as discussed in the previous slide, the source emits two symbols, S1 and S2, with probabilities 3 by 4 and 1 by 4 respectively. So for second order extension, we will have 4 symbols. So total source symbols are 2 in the first order, and the extension is 2. Therefore we'll have 4 symbols, and all these 4 symbols are formed using the first order symbols, that is S1 and S2. So we'll have S1 into S1 as the first symbol, S1 S2, S2 S1, S2 S2. Substitute their corresponding probability values and we'll obtain the total probability. S1 probability is 3 by 4, S2 probability is 1 by 4. Therefore S1 into S1 probability is 9 by 16, S1 S2 probability 3 by 16, S2 S1 probability 3 by 16, and S2 into S2 probability is 1 by 16. So the procedure for Shannon-Fano encoding algorithm is to arrange the given probabilities into decreasing order. So once we arrange the probabilities in a decreasing order, we'll have 9 by 16, and then we'll have 3 by 16, 3 by 16 and 1 by 16 with their corresponding symbols written in the first column. So now we need to group these probabilities into exactly two sets, that is two subgroups, such that both the group probabilities is almost equal. So 9 by 16 is considered as one group and all the remaining in the second group. So first group probability is 9 by 16 and the second group probability is almost equal to 9 by 16. It can be exactly equal or it can be approximately equal. So 9 by 16 one group and all three remaining elements in the second group, and both the group probabilities is almost equal. Hence you can proceed with the further steps. So the first group is assigned with 0 and the second group elements are assigned with 1. So in the first group we have only one element, so further subdivision is not possible here. Whereas in the second group we have 3 elements, 3 by 16, 3 by 16 and 1 by 16. So further subgrouping can be done here. So 3 by 16 one group and the remaining 2 elements in the second group. 3 by 16, 1 by 16 will be in the second group. First group assigned with 0, second group elements assigned with 1. In stage 2, the first group has only one element, so further subdivision is not possible. Whereas in the second group we have 2 elements. Therefore 3 by 16 will be in the first group and 1 by 16 will be in the second group. First group will be assigned with 0, second group will be assigned with 1. So the subgrouping is done till no further division is possible. So now we'll just list out the code words for their symbols and their corresponding probabilities. So S1 probability is 9 by 16 and the code word for S1 is 0. 9 by 16 has the code word 0 and the length is 1 bit. Similarly S2 has a probability 3 by 16. 3 by 16 the code word is written in the left to right direction. So 3 by 16 code word is 1. In the second stage 3 by 16 code word is 0. Similarly 3 by 16 second element 3 by 16 has a code word 10. Similarly third symbol S2 S1 has a probability 3 by 16. So the third symbol which occurs with probability 3 by 16 has code word 1 in the first stage, code word 1 in the second stage and 0 in the third stage. So the code word for 3 by 16 is 110. Similarly for 1 by 16, first stage it is assigned with 1, second stage assigned with 1, third stage assigned with 1. Therefore the code word is 111 and its corresponding length is 3. So now in order to compute efficiency, we need to compute the entropy and average code word length. So since this is second order extension source, the entropy for second order extended source can be written as 2 times h of s, where h of s is the first order entropy which we have computed in the previous slide. The first order entropy is 0.8113 multiplied by 2. Therefore the second order entropy is 1.6226. So we can use this method, or maybe we can refer this table and we can compute the second order entropy. Since we have 4 symbols, summation, lower limit is 1 and the upper limit is 4, probability log of 1 by probability. So first probability is 9 by 16. So 9 by 16 log 16 by 9 term. The next two probabilities are 3 by 16. So 2 into 3 by 16 log 16 by 3. And the last probability value is 1 by 16 log 16 to the base 2. So once you simplify, you'll obtain 1.6226 as the entropy for the second order source, or we may compute using 2 into h of s. Similarly, the average code word length is given by summation I equals to 1 to 4, because we have 4 symbols, probability multiplied by its corresponding length. So 9 by 16 corresponding length is 1, so 9 by 16 into 1 term. Similarly, 3 by 16 into corresponding code word length is 2, so 3 by 16 into 2 term. For third symbol, probability is 3 by 16 and corresponding code word length is 3, so 3 by 16 into 3. And last one, 1 by 16 probability and its length is 3, so 1 by 16 into 3. So once we simplify, we'll get average code word length as 1.6875 bits per symbol. Substitute entropy, average code word length, and we'll get efficiency as 96.15%. So same thing has to be done for a third order extension source. So in first order, source S has 2 symbols, S1, S2. S1 is occurring with a probability 3 by 4. S2 is occurring with a probability 1 by 4. So third order extension will have 8 symbols. So we have 2 symbols in first order source and we are computing third order extension, so 2 raised to 3. Hence we'll have 8 symbols. And the 8 symbols are as follows: triple S1, 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 S2, S1, S2, S1, S1, S2, 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 S1, S1, S2, S1, S2, 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 S1 and triple S2. So all these 8 combinations or 8 symbols of third order extension are formed using the first order symbols, that is S1, S2. Substitute S1 probability as 3 by 4, S2 probability as 1 by 4. Therefore, triple S1 has a probability 27 by 64. Second symbol has a probability 9 by 64. Third symbol has a probability 9 by 64. Next symbol has a probability 3 by 64. S2 double S1 has a probability 9 by 64. And the next 2 symbols are occurring with a probability 3 by 64. And the last symbol has a probability 1 by 64. So in Shannon's Fano encoding algorithm, the first step is to arrange the probabilities in decreasing order. So once we arrange the probabilities in decreasing order, the order is as follows. We'll have 27 by 64 first, next 9 by 64 terms, and then 3 by 64 terms, and the last element will be 1 by 64 term. The second step is to group the probabilities into exactly 2 sets. So if we consider 27 by 64 as first group and all the remaining elements as one group, 27 by 64 as one group and all the remaining elements into second group, and if we compare both the group probabilities, they are not equal. There is a huge difference in the group probabilities. But we require both the group probabilities to be almost equal. Hence, instead of having 27 by 64 in one group and remaining into second group, we have 27 by 64 and 9 by 64 in one group and all the remaining elements into second group. So now both the group probabilities are approximately equal. So first group is assigned with 0, second group is assigned with 1. So in the next stage, the first group has 2 elements. So further subdivision is possible. So 27 by 64 is in the first group, 9 by 64 in the second group. The first group is assigned with 0, second group is assigned with 1. Now further subdivision is not possible. So whereas for second group we have 6 elements. So 9 by 64 in one group, and if I consider all the remaining elements into second group, again the group probabilities are not approximately equal. There is a huge difference. Hence, we have considered 9 by 64 and 9 by 64, 2 elements in one group and all the remaining 4 elements in second group. And now if we compare both the group probabilities, it is approximately equal. So we can proceed with the further steps. So first group is assigned with 0, second group is assigned with 1. In the next stage, this first group has 2 elements. So further subdivision is possible. 9 by 64 is in one group, 9 by 64 is in one group. The first group is assigned with 0, second group is assigned with 1. So in this group we have 4 elements. So further subdivision is possible. So if I consider 3 by 64 in one group and all the remaining 3 elements in second group, again both group probabilities is not approximately equal. There is a huge difference. Hence, we have considered 3 by 64 and 3 by 64 in one group and 3 by 64 and 1 by 64 in the second group. The first group is assigned with 0, second group is assigned with 1. So in this third stage, this group has 2 elements, 3 by 64, 3 by 64. So 3 by 64 is considered as first group and the other 3 by 64 is considered as second group. First group assigned with 0, second group assigned with 1. So in this group we have 2 elements, 3 by 64, 1 by 64. So further subdivision is possible. So 3 by 64 is in one group, 1 by 64 is in second group. First group assigned with 0, second group assigned with 1. So now further subdivision is not possible. Hence, we can list out the code words. So for 27 by 64 the code word is 00. For the second element 9 by 64 code word is 01. For the third element 9 by 64 first stage code word is 1, second stage code word is 0, third stage code word is 0. So the code word is 100. Similarly, fourth element 9 by 64 in first stage code word is 1, second stage code word is 0, third stage code word is 1. So 101. For 3 by 64 first stage code word is 1, second stage code word is 1, third stage is 0, fourth stage is 0. So code word is 1100. Similarly, for the next 3 by 64 first stage code word is 1, second stage code word is 1, third stage code word is 0, last stage code word is 1. So 110. Similarly, we can write it for 3 by 64 and for 1 by 64. For 1 by 64 first stage code word is 1, in the next stage code word is 1, in the next stage code word is 1, and last stage code word is 1. So the final code word is 4 ones, and the corresponding length value is written in the last column. So in order to compute efficiency, we need to calculate what is the entropy and average code word length. Since it is third order extension, the entropy for third order extension can be computed using 3 into h of s. We have already computed the first order entropy in the previous slides. Substitute first order entropy, multiply it by 3, and we'll obtain the entropy for third order extension, which is 2.433. Or using this table, using the probability values, we can compute what is the entropy. The first probability is 27 by 64. 27 by 64 log 64 by 27. The next probabilities are 9 by 64, which is occurring 3 times. So 3 into 9 by 64 log 64 by 9. 3 by 64 is occurring 3 times. So 3 by 64 log 64 by 3. And the last one is 1 by 64. 1 by 64 log 64 to the base 2. Once you simplify, you'll get 2.43 bits per symbol. Either you can use this method, which can be done by referring this table, or using 3 into h of s. Based on the derivation we did it for nth order extension. For nth order extension, the entropy is given by n into h of s. Similarly, for third order extension, n value is 3, so we'll have 3 into h of s. So we need to compute average code word length. We have 8 symbols in third order extension, so summation limits are 1 to 8 pi into li. So multiply probability value and its corresponding length. So first one 27 by 64 into 2. Similarly 9 by 64 into 2. 9 by 64 into 3. Next we have again 9 by 64 into 3. and then 3 by 64 into 4, 3 by 64 into 4, and the last one is 1 by 64 into 4. This should be 1 by 64 into 4. So 3 by 64 is occurring 3 times. So we'll have 3 terms, 3 by 64, 3 by 64, 3 by 64. And last one is 1 by 64. So this term will not occur. Once we simplify, we'll obtain average code word length as 2.59375 bits per symbol. And once we substitute entropy and average code word length, we'll obtain the source efficiency as 93.84%. So in the previous slides, we have determined codes for the discrete symbols using Shannon's Fano binary encoding algorithm. For binary encoding algorithm, the code alphabets are 0 and 1. So now we'll discuss Shannon's Fano ternary encoding algorithm. For a ternary encoder, the code alphabets are 0, 1 and 2. And the procedure for ternary algorithm is similar to binary. So first arrange the probabilities in decreasing order. Second step, group the probabilities into 3 groups. Since it is ternary, 3 groups. In the previous concept it was binary, only 2 groups. So group the probabilities into 3 sets such that sum of the probabilities in all 3 groups is approximately equal. Assign 0 to the elements of first group. Assign 1 to all the elements of second group. Assign 2 to all the elements of third group. And repeat step 2 by dividing each group into 3 subgroups till no further division is possible. So the problem statement is as follows. Construct Shannon's Fano ternary code for the discrete symbols and their probabilities listed below, and also compute code efficiency and draw the corresponding code tree. So the first step is to arrange the given probabilities into descending order. So the order is 0.3, 0.3, 0.12, 0.12, 0.06, 0.06, and at last we'll have 0.04. So we need to group these probabilities into 3 sets. 3 sets for ternary, whereas 2 sets for binary. And all the 3 group probabilities must be approximately equal. So 0.3 is considered as first group, second 0.3 is considered as second group, and all the remaining elements as third group. So all 3 group probabilities are approximately equal, and the first group is assigned with 0, second group is assigned with 1, third group is assigned with 2. So for the first 2 groups, since they have only one element, further subdivision is not possible here. Whereas in the last group we have 5 elements, so further subgrouping can be done. 0.12 is considered as first group in the next stage, 0.12 is in the second group, and all the remaining 3 elements in the third group. And if we compare the group probabilities, they are approximately equal. and the first group will be assigned with 0, second group is assigned with 1, third group is assigned with 2. In the second stage, for the first two groups, since they have only one element, further subdivision is not possible. Whereas in the last group we have three elements, so further subdivision can be done. 0.06 is in first group, 0.06 is considered as second group, and 0.04 is considered as third group. First group is assigned with 0, second group assigned with 1, third group assigned with 2. So now we can list the code words. For the first 0.3 element, code word is 0 and its length is 1 bit. For the second 0.3 element, code word is 1, length is also 1. For 0.12, the code word assigned in first stage is 2, second stage is 0, third stage is 0. So code word for the third element S3 with probability 0.12. So for the third group in the first stage, all the elements are assigned with code word 2. In the second stage, for this third group, all the elements are assigned with code word 2. So 0.12 code word is 20. For the next 0.12 code word is 21. For the next one, code word is 220. For the next one, 221. For the last element with probability 0.04, code word is 222. And the corresponding bit length is represented in the last column. So coming to code tree, so as discussed in the previous lectures, if it is a binary decision tree, at every decision point we'll have two bifurcations. One is for 0 and one is for decision 1. If it is ternary, at every decision point we'll have three branches: decision 0, decision 1 and decision 2. So coming to the decision tree, so at initial point we'll have three decisions: 0, 1 and 2. So 0 code word will attain a terminal state S1, 1 code word will attain a terminal state S2. So next code word is 20. So it begins with 2. So at 2 branch we'll have a decision point with three decisions, that is 0, 1 and 2. So 2, 0 will attain terminal state S3 and 2, 1. So this branch 2, 1 will attain terminal state S4. So next we have 220. We already have 22 here. So at this 2 we'll have three decisions since it is ternary. So decision 0, 1 and So double 2 2, that is triple 2 will attain terminal state S7. Similarly 2 2 and 1 will attain terminal state S6, and 2 2 and 0 will attain terminal state S5. So if it is a binary decision tree, we'll have two decisions, decision 0, decision 1. If it is ternary, we'll have three decisions, decision 0, 1 and 2. If it is quaternary, we'll have four decisions. Similarly, in order to determine code words using binary algorithm, we'll have two groups with approximately equal probabilities, group 0 assigned with 0 and the next group assigned with 2. If it is ternary, we'll have three subgroups, first group assigned with 0, second group assigned with 1, third group assigned with 2. If it is quaternary, we'll have four groups with the group probabilities approximately equal, and the first group will be assigned with 0, second group will be assigned with 1, third group will be assigned with 2, and the fourth group will be assigned with 3. And this subgrouping is done till no further subdivision is possible. So in order to compute efficiency, we need to compute entropy and average code word length. So we have 7 symbols. So summation limit is 1 to 7, probability log of 1 by probability, and the base is 3 since it is ternary algorithm. If it is binary, it will be 2. If it is quaternary, it will be 4. Since it is ternary, it is 3. So 0.3 log 1 by 0.3 to the base 3. Similarly 0.3 log 1 by 0.3 to the base 3. 0.12 is repeated 2 times, so it can also be written as 2 into 0.12 log 1 divided by 0.12. Similarly 0.06 is occurring 2 times, 2 into 0.06 log 1 by 0.06, and the last one 0.04 log 1 divided by 0.04. So once we simplify, we'll obtain entropy as 1.542, and the average code word length is given by probability into its corresponding length. So 0.3 and length is 1. Similarly next one is also 0.3 and length is 1. For the next two, it is 0.12 and length is 2. So 0.12 into 2, 0.12 into 2. For 0.06, the corresponding lengths are 3, and 0.06 is occurring 2 times, 2 into 0.06 into 3. Last one 0.04, length is 3. Once we simplify, we'll get 1.56 as the average code word length. Substitute entropy and average code word length, and the efficiency will be 99.05%. Thank you.